Okay, folks, so this is a problem that was on the week 2 quiz for the IFSTA book, and this tripped a few people up, so I want to spend a little bit of time reviewing it. The scenario they're asking you about in this question is a steel beam that's being protected from fire by a gypsum coating. So the story with steel is it's a great structural material, but at 1,000 degrees it's only about 60% of its cold strength. So we have to somehow protect the beam from the fire. Here's one configuration you might find. You might find a box beam in which the perimeter is equal to 40 inches. So if we think about maybe a typical box beam, it'd be something like 15 inches by 5 inches. If we add the four sides up, 15 plus 5 plus 15 plus 5, you get to 40. Another more typical configuration might be a wide flange beam. You'll hear these called I-beams, which they really are not. The correct term is wide flange. I-beam is a beam that looks similar, but was an older technology. So pretty much wide flange beams are universal in construction now. Now, this doesn't have an obvious perimeter, but basically the perimeter becomes the area that would be covered by the drywall or gypsum coating, which in this case would be equivalent to 40 inches. So basically a 15 by 5 by 15 by 5 beam that's covered by gypsum, which I've shown in green here. And we'll just label this as 15 inches and 5 inches. Now, the formula is going to calculate the fire resistance of the beam in minutes. So that's what we're trying to get to, is some number of minutes. So if I write the formula out here, R is what we're solving for in some number of minutes. And then you'll notice that we have several sets of brackets here, and that's because order of operations becomes important in this calculation. So we're going to redraw the brackets just as you see them in the formula. And then C1. C1 is a constant that's calculated by taking 1200 divided by the insulating material density. And I don't know how they derive this 1200, although I'd be willing to venture that because the material density is expressed in feet, but the thickness of the coating is expressed in inches, we probably need to do a conversion by a factor of 12 to make the units work out. So we're going to have to solve for C1 before we can finish writing out the formula here. So let's write out C1 equals 1200 divided by the material density. So let's see if they give it in the problem. Yep. The insulated with a material equal to density equal to 40 pounds per cubic foot. So 1200 divided by 40. And normally we would like to associate units with this, but some of the information the text is given is incomplete in terms of the units of some of the terms. So in this case, we're just going to get the number. So 4 goes into 12 3 times, 40 goes into 1200 30 times. So we're going to come over here and we'll get that mark off of there, and then we'll write in 30 in place of C1. Then what are we doing? We're multiplying it by M. M is the mass of the beam in pounds per foot, which in this case is given as 60. So the story with beams like this is that you might imagine that they could make this beam with webs and flanges, webs and a flange of any thickness really that you'd want. And so to describe how thick the metal is, typically this beam would be sold as a 15-inch by 5-inch wide flange beam at a weight of 60 pounds per foot. You could buy the same beam maybe at a weight of 30 pounds per foot, which would be a lighter and less strong beam. So we're going to put the mass in pounds, which is really kind of a misnomer because pounds is a unit of weight, not a unit of mass, but it's not going to affect the calculation. Then to that product, we need to add C2. And C2 is basically an engineering constant that describes how well gypsum resists fire. And again, they don't give us any units for that, but basically what you need to understand about it is that a higher number means greater fire resistance. So wood, for instance, a wood panel maybe has a C2 of 30, maybe even 15, substantially less resistant to fire. Then we're going to close this with a square bracket. Then we're going to multiply by I. And in this case, I is the thickness of the protective coating, and that should say in inches. So it's covered in 1 inch thick gypsum, so times 1. And then this entire expression gets divided by, actually I guess I need to close this, close the set, and then the entire expression gets divided by the perimeter of the beam in inches, which again is 40 inches. And it may seem a little counterintuitive. The perimeter of the beam ends up in the denominator of the equation, which means as the perimeter gets larger, the effective fire resistance of the beam becomes less. But if you think about it, it does make some sense, because as the perimeter of this beam becomes larger, there's more surface area exposed. Also, if the perimeter becomes larger without any of these other numbers changing, that basically means that the beam per foot weighs the same amount, even though it's a larger beam, which means the metal is thinner. So, on examination, it does make some sense that you'd end up with that. So you'll notice that we've replaced all of the letters with numbers. Now it's just time to turn the crank on this. So R equals, well, 30 times 60, that's 1800. So we'll draw our brackets. 1800 plus 72 times 1, all over 40. Ooh. Well, 1800 plus 72 is just 1872, and times 1 is just 1872. So again, we end up with the resistance of this beam is 1872 over 40. Now that number is not easily calculated, but we can plug that into the calculator and come up with a number. If I think about approximately what ballpark it would be in, well, 40 times 40 is 1600, 40 times 50 is 2000, so I would expect that the result I get from this division is going to be somewhere between 40 and 50. And you can see that we get a number of 46.8, which is reasonable. Now, we got to think about what are the units here. Well, the formula tells us that R is given in minutes. So this beam has got a fire resistance rating of about 47 minutes. And in fact, if you read the directions on the test actually wants you to round to the nearest minute. So we'll do is approximately equal to 47 minutes. Now it's important to understand it doesn't mean that this beam is going to come crashing down 47 minutes into the fire. It means that in a laboratory setting, they were able to keep the beam at a certain temperature under a given fire load for 47 minutes. I hope that makes this question a little bit more clear. If you have any other concerns or questions about it, please feel free to get in touch with me and we can discuss it further.